Okay, hello. Now, we're going to talk about chemistry again. Last time, right, the last day 4 of learning with me, we had discussed about group 1, which meant that in the periodic table, these chemicals were over here. I'm sorry, my screen's a bit far. I'm going to zoom in real quick. Sure, that'll work. We're talking about group 1, which were chemicals that were arguably, probably very reactive. And they were placed in group 1 of the periodic table because they had only one valence electron. Okay, but today we're talking about something different. We're talking about group 17, not group 18, because 18 is the argon gases, the noble gases, not the argon gases, the noble gases or the inert gases, which are incredibly unreactive, and they are fundamentally very different from the other elements, and we'll discuss that in another day. But today we're going to talk about group 17. So before we move on, we have to know what are the elements in group 17. Now, we have, normally for group 1 and group 18, you memorize the first three, which is for group 18, it is helium, neon, and argon. For group 1, it is lithium, sodium, and potassium. For group 17, however, we should usually memorize the first 4, which contain fluorine. Fluorine symbol is, yes, fluorine, chlorine, fluorine, chlorine, bromine, and lastly, what's the last one? Lastly, we have iodine. Okay, so for these 4, they usually give examples for these 3 the most because fluorine is incredibly light and you won't see it that much. But regardless, you should know about these 4 elements. And of course, they're not the only ones in here. There are also, this is astacine, and lastly, tennessine, something like that. These 2, I think they're alright, they're not that important, but you should just know them just for fun's sake. Okay, so the first thing I'm going to talk about is first, how we all have a name for these groups, right? For group 18, they're called noble gases. For group 1, they're called alkaline metals. So for group 17, first of all, they have 7 valence electrons. Then for group 17, they are known as halogens. I say halogens because, hello. Okay, so they also exist as diatomic molecules. Diatomic in the sense that there are 2. So all of these gases, because they're on the gases side, they're in the non-metals, they all need a 2 at the end. So fluorine 2, chlorine 2, bromine 2, compared to monoatomic elements are, example, helium, He, neon, Ne. No need for 2 because they're already stable. The 2 here is to ensure that these atoms are stable. Not atoms, these elements. Okay, so going on to our halogens, you can get to know your textbook. They give you some uses about them. Going through it briefly, chlorine can be used in bleach. Because it has a bleaching property, then bromine it can be used in fire extinguishers. Iodine can be used as a disinfectant. That's alright. We're going to talk about some actual important things like the physical properties of things in group 17. So first and foremost, they give you a graph over here on page 93, and they say, okay, going down group 17, the physical state of halogens at room temperature changes from gas to liquid to solid. Now, according to that table, they feature chlorine, they feature bromine, and they also feature iodine. Okay, can you see? Yes, you can. They don't give you the rest, and they give you the state of matter. So this is gas, this is a liquid, and this is a solid. Now, just from here, you don't have to memorize the rest because you can predict already. If iodine here is a solid, then going down would be, it would be acetylene, something like that, acetylene. And if it's already a solid here, that means association will also be a solid. Same thing here for chlorine. Above here is fluorine. Fluorine is going to be a gas. Alright. So then they give you a graph about their melting point and their boiling point and their density. So all you have to know is that their melting point, it is as you go down, the melting point increases. That means over here it's negative 101 for chlorine, but for iodine it's 114. Okay, for the boiling point for chlorine it's negative 34, negative degrees Celsius. Then for iodine it's 184 degrees Celsius. And for density, over here it is 0.0003, and over here it is 4.95. So as you can see, everything is going on an increasing scale. Then they explain it to you. So going down the group, the increase in molecular size will cause the attraction force between molecules to become stronger. Okay, what are they going on about? Let's look over here. The melting point and boiling point of will increase because more heat energy is required. Okay, so it's like this. Doom. Let's talk about, let's draw chlorine for example. Cl. Okay, this is 1, 2, then a bigger one. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, can you see that? Okay, good enough. Alright. So, increase in molecular size. So, chlorine is this size. Then, okay, I've actually drawn chlorine a little bit big. But now let's imagine if bromine was here. Okay, bromine. The bromine has a lot of shells. So, you can imagine just how big bromine would be. So it's humongous compared to chlorine. Now, you're saying that the melting point and the boiling point of halogens will increase because more heat energy is required to overcome the intermolecular forces. What are intermolecular forces? You can understand them as the... Sorry, I'll have to draw this. Okay, say goodbye to my very beautiful diagram. Ding, 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 ding. To understand intermolecular forces, imagine you have a Cl molecule here, Cl molecule here, then you have 2 more here, example. Okay, the force between these molecules is what you call an intermolecular force. Now Cl is here, then you can imagine if I had bromine, it would be significantly larger. Okay, well, they're not supposed to intersect like that, but you get the idea. If Cl is this small, then bromine would be a lot larger. Okay, then continuing onwards, we're saying more heat energy is required to overcome this intermolecular forces, and the density of the elements also increase with the increase in the mass. Okay? That's all. Then, when they were explaining group 17, remember, for group 1, what were their characteristics? Group 1, they were all shiny, like metals. They had like a shiny gray color. What about group 18? The noble gases, they were all colorless gases. For group 17, the halogens, they're a little bit special in this sense. They're a bit gay. They all have different colors, have special colors. So, they say over here, for chlorine gas, it's a greenish yellow. For liquid bromine, which is bromine, it is a reddish brown. And for solid iodine, it is a purplish black. Okay, so yellowish green, reddish brown, and a purplish black. Then the question is, what will they do in the examinations is that they could ask you, they want you to predict. Okay, example, I put X here and then I put chlorine here. And I give you the characteristic, this is a yellowish green. And I want you to tell me what is the possible, like what is the color of element X that is part of group 17, the halogens. So, well, actually over here we know it is fluorine, and they do give it to you in the textbook on page 95 that fluorine is a light yellow color. Now, say you don't know, all you have to do is predict that the colors are going darker, right? So over here it will be a lighter color, hence light yellow. But say we do the opposite. Say I don't put chlorine here, I don't put X here. Let's say I put bromine here instead. So bromine is a purplish black, and I put the color, I put the unknown X. Okay, predict the color of X. You know that bromine gas turns purplish black. It's only right to assume that it's going darker from a light yellow to yellow green to reddish blue to purplish black, all the way to the most black, to the darkest color possible, just black. There's no need to add very black, dark black, because black is already a dark color. Alright, so that's what they could possibly ask you about these colors. Alright, now moving on, we can talk about something a little bit more interesting, according to me, which is their chemical properties. So if you remember, for group 1, we learned that, okay, group 1, how do they look like? They look like 2.1, like this, right? 2.1, 2.8.1. Their valence electron is a 1. Okay, so in this scenario, for example, 2.1, ding ding, okay, 2. Okay, you know what, I'm gonna draw 2 here, an even smaller circle here, okay, like this. Okay, you have an interesting element here that looks like an egg. 2, 1. Okay, so you have 3 electrons. Then the question is, alright, how do we check the reactivity is how the tendency of the atom is a very important part in chemistry. Always mention it when you're answering questions. Atom, okay, A-T-O-M-E. A-T-O-M. And Adam, if you're watching this, hi. So, over here, if we want to check how reactive it is, it's according to the tendency of the atom to either donate, to accept, or to share electrons. So in a situation like this where it's 2.1, what is the most convenient way to make it a stable atom, a stable element, is to make it into either a duplet, can you see that? Yes. A duplet electron arrangement, which is where you have like 2 for like helium, or instead give it an octet arrangement where it's an 8, so like 2.8.8, 2.8. Alright, so what we'll do in this scenario is that you have 2 options here. You can either you can either accept or receive 7 electrons to form an octet arrangement, or donate 1 electron. So that is the most convenient way. But for group 17, it's the opposite. They have 7 as their valence electron. Meaning, in this scenario, this is what it would look like. 1, 2 here, then boom, 1, 2, 3, 4, 5, 6, 7. Okay, 7. So instead of donating 7 electrons to a whole different element, what is the most convenient way and the most efficient way? It is to instead receive 1 from someone else. So you can see they write it over here, X plus E negative. That means X received. X is the atom. So the atom receives 1 electron and it will form a negatively charged ion. Alright? Why would it form a negative charge ion? Because in here you have 7 protons, right? That's why you get 7 electrons. So 7 protons, when you receive 1 extra electron, in an atom, protons and electrons are equal. 7 electrons. But now that I've added 1 extra electron, it is now negatively charged because you have 8 electrons and 7 protons. Okay? That is that. Now I'm gonna rub this off. Okay, then if you go into your textbook, they start talking about reaction of metals and alkali, and I'm gonna come back to this later when we talk about the experiment. For now, let's go into the changes in reactivity, alright? So talking about reactivity, we already stated it's because of the valence electron tribe, but we can go even deeper to talk. Okay, did you know that the reactivity of elements describes when going down group 17? Increasing atomic size will cause the valence shell to be further from the nucleus. This will cause the nuclear attraction force towards the valence electrons to become weaker, thus difficulty in attracting electrons. Okay, what is it on about? See, say I have chlorine here. 2. Okay, say I have chlorine, and then I have, okay, just imagine iodine's here, right? Just imagine a very, very, very big element of chlorine. Okay, what I'm trying to tell you is that first thing you must compare is the atomic size. Who is bigger in this situation? It's kind of obvious, right? According just to the density itself, chlorine is significantly larger than, sorry, is this chlorine? No, iodine is significantly larger than chlorine is. So if we're trying to answer the question, they might ask you, okay, we can ask you, okay, between chlorine and iodine atoms, which is more reactive? State your reasons or explain. So you can say first, compare. Iodine has a larger atomic mass compared to the chlorine atom. Okay, then why does this matter? Well, first, this atomic size, right, will cause the valence shell to be further from the nucleus. But as the valence shell is where you will see your valence electrons. Over here, it's this outer shell. And your thing about the nucleus is because if you look over here in this diagram, say the valence electron is here. This shell in particular is very far away from the nucleus compared to here. Like this is the small distance, it's only this much. But over here it's like, whoa, that's a big distance. So what is it far away from? The nucleus. And what is in the nucleus? The proton. The proton is what's really affecting all of this nuclear attraction force, okay? Your NAF, it's all from the protons, okay? So this will cause the nuclear attraction force to become weaker. Meaning, the bigger you are, the weaker your weaker your attraction force. Okay, the weaker your nuclear attraction force towards the valence electrons. All right. Thus, you will have that means that iodine. I have to write this down. Iodine. Jeez. Okay, that means iodine will have a much harder time trying to attract another electron to join its, little party here compared to chlorine. Cool? We're cool here? The larger you are, the weaker your nuclear attraction force towards the valence electrons. Thus, you have a harder time trying to attract one extra electron to form either an octet or a duplet electron arrangement. Amazing. Then, of course, at the bottom here, they've given you some extra information about stuff in group 17. So here it says, all halogens are soluble in organic solvents like alcohol and petrol. They do not conduct heat nor electricity. But we have some exceptions. Something like fluorine is a light yellow poisonous gas. It's very reactive. Remember, why is it very reactive? Think about it. If chlorine is already so small, imagine how teeny fluorine is. Fluorine is teeny as well. Alright, so the smaller you are, again, the smaller the atomic size, then the distance between the nucleus and the valence shell is smaller, and thus the nuclear attraction force towards valence electrons is stronger, making it easier for you to accept an extra electron from other elements. So it's very reactive and corrosive. We'll go into this on why, but corrosive things are usually acidic, and we'll go into why it's acidic in the experiment. Then it will cause a strong explosion when combined with hydrogen gas, blah blah blah, and then they mentioned acetylene. Okay, acetylene is a rare radioactive gas. That's about it. Not much there. Now going on to the reactions, right? I'm gonna rub this off real quick. Okay, we're almost ending everything we know about the halogens, which is, chlorine, bromine, and iodine have the same chemical properties but different reactivity. Exact same thing with group 1. Same chemical properties but different reactivities. Why different reactivities? Because of the number of shells. And why do I say that? Because the number of shells are directly influencing their size. And when you influence specifically their atomic size, when you influence their atomic size, what you're influencing? Ding, ding. You're influencing how far away the valence shell is from the nucleus, thus influencing the nuclear attraction force towards valence electrons. Okay? Ding, 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 ding. We're gonna stop repeating this. Hold up. Okay, what is it actually trying to say? When halogens react with water, okay, they're gonna test two things. Test with water. My water is kind of gay. What the freak? Water. And what's this? Sorry. When halogens react with water, an acidic solution is formed. Therefore, put this in perspective. When we talk about group 1 metals, lithium, sodium, and potassium, they were considered alkaline metals. These are acidic solution, not really metals, acidic non-metal elements. So, for example, the reaction of chlorine with water will produce hydrochloric acid and hypochlorous acid. So, you look at the symbol here, it's like Cl2, okay, gas, I won't write that, H2O. Okay, they put this symbol. Small reminder, this is a symbol to indicate that the product here, HCl plus, okay, I will be blocking it, hold up, HCl plus H, hypochlorous acid. This is a reversible process, meaning the products here can form back to what the reactants were. Right. So when halogens react with metal, a metal halide is formed. Halide, apa tu halide? Did you know that if you notice group 17, we always mention group 1 when we talk about group 17 because we take group 17's non-metals to react with the metals in group 1. For example, sodium, Na, belongs in group 1. For example, chlorine belongs in, chlorine should be a 2, negative, plus, okay. Chlorine belongs in group 17, a halogen and an alkaline metal. Extremely reactive, alright, you will get sodium chloride. Sodium chloride, which is the normal salt that you eat, if I'm not wrong. Normal is like table salt. Another example, can I think of anything else? Sodium. Basically, yeah, you can see the I here, right? Chloride, it was chlorine. Now it became chloride. Example, it's the same thing for other sulfide. Example, we have bromine, it will become bromide. Okay, so you can think of the halide like that. The halide over here, halogen, halide. They're considered group 17 because they are non-metals. They're considered anions. There's the cations and the anions. So they are at the back of the quote-unquote equation, you can call it. So that is what you need to know. They give you an example where they have the reaction of, they have, what is this? Iron with bromine and produces iron 3 bromide. Okay, then they say when halogens react with an alkaline solution, metal halide, metal halate, and water is formed. Okay, halide, ide, no oxygen, ate, banyak oxygen, lots of oxygen, and water will be formed. For example, that equation, iodine with sodium hydroxide. So you might be thinking, why are they reacting with an alkaline solution? Why not something acidic? Very simple. Because group 17's halogens are acidic in the first place. Thus, they will react with alkaline substances. That's why we take group 17's chlorine, and you react it with sodium from group 1, which is alkaline. Alkali and acid, boom, together. Alright, and that's about all for group 17. But since I want to also go through a little bit of period 3. Okay, period 3 will be a little bit different from group 17 because groups are going down. We're talking about valence electrons. Now, for period 3, they have different valence electrons but the same number of shells. So let's go into that, shall we? So we only learned period 3. We only learn period 3 in this Form 4 syllabus, and they can sometimes relate this to period 2 because they are quite similar. Okay. Now, actually, I think this video will be quite long, so you know what, we're just gonna focus, just get to know this and who is part of this group. So you have sodium. Hey, sodium, you have your magnesium, aluminium, silicon, don't have space anymore, phosphorus, then you have, is it neon? No, sulfur, chlorine, then argon. These are your elements that are part of period 3, and I think that's what I'm going to go through. That's only what I'm going to go through. So again, because it's getting late, I need to sleep. So period 3, bye-bye. So the recap, we have now learned, I have a video on group 1, I have a medal on group 1 metals, and now a video on group 17 metals. Thank you, this was Chemistry with Jonathan Rizal. Goodbye.